off with the fundamental theorem of calculus. And if you notice, we spent probably about 10 or 15 minutes kind of going through the proof of it. But the first part of the fundamental theorem of calculus says that if I have a function f of x equal to this this integral, basically, remember we said that x moved between a and b, and we had these different areas, and we gave that a function. Okay, and so then if you take the derivative of that, it actually becomes the function f of x. And so this is a big deal because it ties together the idea of integration and derivatives. All right? Is that basically, by looking at this, we can say that an integral is the inverse of a derivative, or the antiderivative. Okay? So it's kind of a big deal. And you can see that in the name of the theorem, that it is the fundamental theorem of calculus. That this is one of the big things in calculus, that if this is true, then integration, which we're going to see can lead to a lot of different things, not just area under a curve. Okay, well, it is area under a curve, but we can relate that to a lot of different things. That integration is going to be just as powerful as derivatives were. Okay? So I think in our, I can't remember where we left off in our proof. So I think we'll just start, I'll just start really quick and go through the first part of it really quickly. And basically we said, okay, let's go ahead then, if we want to find the derivative of f, we're just going to use the definition of a derivative is equal to the limit as h approaches 0 of capital F of x plus h minus capital F of x divided by h, right? And then we plugged in x plus h into this, because this is how we defined f of capital F of x. So then we said the limit as h goes to 0 of the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt, and then all this divided by h, okay? Then we said that we had the limit as h goes to 0 of f of a to x of f of t dt plus f of x to h of f of t dt minus the integral from a to x of f of t dt. And we said this because we use that kind of transitive property of integration. If I go from a to b and b to c, that's the same thing as a to c. And then when you look at it like this, just algebraically, those two integrals cancel out. So I was just left with the limit as h goes to 0 of 1 over h times the integral from x to h of f of t dt. Okay? And so we looked at this and we said this is just the average value of this. We said we used by the average value of the function, which was 1 over b minus a of the integral from a to b of f of x dx, okay? And then we started talking about the average value. And then by the mean value theorem, there had to exist some c, didn't there? There had to exist some value between x and h such that it was equal to f of c, that there is some c that equals f of c. So really, and then we started to talk, is this where we left off? I can't remember. Where did we leave off? Right there. We left off right here. Okay. And so then this one, basically you think about it, that we said there's some value of c in between here, okay? By the mean value theorem. There's some value of c here. So, if you remember, and then x would be any value, and then h would be here. But as h goes to 0, what happens to h what happens to this thing as h goes to 0? It gets closer to x, doesn't it? Okay? And so we're saying that there's some value of c in here, all right, that, well, let me do this. So there's some value of c that this thing is equal to. So really what we can say then is that we're actually looking at the limit as h goes to 0 of f of c. Okay? The average value of that thing is going to be equal to f of c. Okay? Whatever that kind of midpoint is. But then as h goes to 0, what's happening to x and h? As h goes to 0, what's happening to x and h? H is basically getting closer and closer and closer and closer to x, isn't it? Okay. So really, what happens here is as h goes to 0, this function just becomes f of x. Yeah.
If h is approaching 0, like on that graph, wouldn't it eventually pass x as it goes to 0?
No, h is just the distance.
Oh, between x.
Yeah, because actually this point right here is x plus h.
Oh, okay.
Does that make sense?
Yeah.
Yeah.
Thank you.
Yeah, the way I had it written, yeah, you're right.
Okay.
Yeah, that's x plus h. Because that's, remember how we set that up? Okay. So that's x plus h. Yeah, thank you, Olivia.
So in your integral that you were writing up there, it's x to x plus h? Is what you,
From here?
down,
No.
over one, oops. Over,
No.
Yes, up at the top.
No.
It's just h.
It's h, because basically we're saying the integral from a to x, right?
Okay.
And then this little distance here is h units.
Oh,
Okay.
I get it.
Does that kind of make sense?
Yeah, thank you.
Yeah. So, yeah. Yeah, I'm sorry, you're right, that should be x plus h. You're right.
Oh,
You're right.
okay.
You're right. Yeah, that should be x plus h. Yes. Thank you, Olivia. I think I had it right on Friday.
Yeah.
I just kind of zoomed through it. But basically what's happening now is as h goes to 0, it behaves just like x. And so as h goes to 0, here it is. It is the function. And so we've basically proven that the derivative of the integral is the function. Okay? The derivative of the integral is the function. So one thing, just notation-wise, by the way, as we kind of continue on and we keep looking at stuff, it took me forever to figure this out too, by the way. I went all the way through calculus in high school and didn't quite really realize this. But when you see capital F, okay, capital F kind of, it means that's the antiderivative of F, okay? So when I start to write out some other things here, keep in mind that capital F and lowercase f are two separate things, but they're kind of related, okay? So kind of keep that in mind. So that's the kind of the proof of it there. Yeah, let me see if I got. Did I get everything there? Yeah. Okay. So this is part 1.